All right, let's get right into it. Today, we're not just talking about the next G in cellular tech. We're going to tear down and rebuild our understanding of what a network core even is. Because the 5G core, it's not just an upgrade, it's a full-blown revolution. A complete shift from clunky, rigid hardware to a smart, software-driven world. And honestly, this changes absolutely everything about global connectivity.
Think about this for a second. We're talking about a world where literally everything is connected. I don't mean just your phone. I mean your car, the factory down the street, the farm equipment in the field, entire cities, all online. Billions upon billions of devices, and every single one of them is screaming for a piece of the network.
And for these things, fast enough just doesn't cut it. We're talking about communication that has to be perfectly predictable, deterministic. You've got a surgical robot being controlled from miles away. That needs single-digit millisecond latency. No excuses. A self-driving car's control system. It needs data now. See, this isn't just about getting a faster download speed for a movie. It's about reliability and low latency becoming a fundamental, non-negotiable part of the service. So that's the future we're trying to build, right? A network that can handle all of this at a planetary scale without breaking a sweat. And here's the problem. Our old networks, they just weren't built for this. For all the amazing things 4G did, its architecture eventually just hit a wall, a hard, unbreachable wall. Okay, so let's talk about that wall, the 4G wall. What was it? Well, it was the 4G Evolved Packet Core, the EPC. And look, it was a masterpiece for its time, no doubt, but its design, man, it was all about dedicated physical boxes and super rigid point-to-point connections. And that right there, that became the ultimate bottleneck. It just choked off innovation and made it impossible to scale the way we needed to. I mean, the difference in philosophy here is just night and day. On one hand, you have the 4G EPC. Think of it as one giant monolithic block. Every function was tied to a specific piece of hardware. If you wanted to scale up, you had to buy more boxes, a huge, expensive physical process. And rolling out a new service? You were looking at months, maybe even years. 5G just blows that whole model up. It completely disaggregates everything, and instead it borrows its playbook from the world of cloud computing and hyperscalers. And that's what this section is all about, the cloud-native revolution. This is the heart of 5G's solution. And let's be super clear. This isn't just about taking the old software and running it on a server. No way. This is about completely rewriting the network's DNA from the ground up, using the principles and the language of the cloud. Okay, take a look at this. What you're seeing here isn't just another network diagram. It's a total paradigm shift. You see that tangled web of connections from the 4G world? Gone. Instead, you have these clean, independent network functions talking to each other through a central, software-driven message bus. This, right here, is the service-based architecture, or SBA, and it is the absolute heart of the 5G core. So what is a service-based architecture? Think about it like this. In the old days, the network software was one giant monolithic program. If you wanted to update one tiny part, you had to take down and redeploy the whole thing. It was a nightmare. SBA breaks that giant program into a bunch of smaller, independent microservices. For example, you've got one service, the AMF, that handles your connection and when you move around. You've got another one, the SMF, that manages your actual data session. Each one is its own little program, exposing what it can do through standard APIs. It's like a modern cloud app, not an old-school piece of software. And the way they all find each other is just beautiful. It's called dynamic service discovery. So when a new network function comes online, the first thing it does is announce itself. It registers its skills, what it can do, with something called the Network Repository Function, or NRF. Think of the NRF as a directory or a matchmaker. Later, when another function needs something, let's call it the consumer, it just asks the NRF, hey, who can do X for me? The NRF points it to the right producer, and they start talking directly. This loose coupling is the secret sauce. It's what allows for automatic scaling, insane resilience, and pushing out new services at lightning speed. So, the SBA doesn't exist in a vacuum. It's built on a few key cloud-native ideas. First, those microservices we talked about, they live in containers, which makes them super agile. Second, and this is huge, is SUPS, control and user plane separation. Basically, you split the network's brain, which is all the signaling and control, from its muscle, which is the part that actually moves your data packets. Why do this? So you can push the muscle out to the edge of the network for super low latency and scale it separately from the brain. And third, you make the function stateless.
That means they don't hold on to session data, which makes them way easier to scale and recover if one fails.
Okay, so we've got this awesome, flexible, scalable software core. So what? What can we do with it that we couldn't do before? Well, this is where it gets really interesting. We can now do something called network slicing, basically carving up the physical network into custom-built virtual networks on the fly.
And that brings us to this central puzzle. How on earth can a single physical network handle 3 completely different jobs at the same time? You need a massive pipe for high-speed video, you need a rock-solid, zero-latency connection for a self-driving car, and you need to support millions of tiny, low-power IoT sensors. You can't have one network that's perfect for all 3 of those, right? A one-size-fits-all approach just fails.
The answer, of course, is network slicing. It's the magic trick that the 5G core enables. You take one big physical network and you digitally slice it into multiple virtual networks. The key here is that each slice is its own little world. It's a completely self-contained, end-to-end logical network with its own resources, its own rules, its own performance guarantees, all perfectly tuned for whatever job it's supposed to do. And 3GPP has defined 3 main flavors of these slices. First, you have eMBB, Enhanced Mobile Broadband. That's your high bandwidth slice for things like streaming video. Then you have URLLC, Ultra Reliable Low Latency Communication. That's the one for your self-driving car or remote surgery, where delay is not an option. And finally, MMTC, Massive Machine Type Communication, which is all about handling a crazy number of connections, like for all those IoT sensors. And the most important part, what happens in one slice stays in that slice. They don't interfere with each other, even though they're all running on the same hardware.
Okay, this all sounds amazing, right? Flexible, programmable, powerful, but there's a catch, and it's a big one. This revolution in openness, this whole new API-driven world, it creates a massive new security problem. By breaking apart that old, closed-off box, we've just created a huge, expanded threat surface. Every one of those new APIs, every microservice, it's a new door for an attacker to try and open. It's a classic case of a double-edged sword, really. The 5G core's greatest strengths are, ironically, its biggest security headaches. Those open APIs that let us innovate so quickly, they're also new ways to attack the network. Running everything in a shared cloud environment, that opens the door to risks we never had to think about with our old, isolated hardware. And those billions of cheap IoT devices, yeah, a lot of them have terrible security. Then you've got the user plane pushed out to the edge. Suddenly, you have to protect data everywhere, not just in one secure central location.
So how do we fix this? Well, the old way of doing security is completely dead. That whole idea of building a strong wall around your network, the castle and moat approach, it's useless now. Why? Because there is no perimeter anymore. The network is everywhere, it's distributed, it's dynamic. So to defend it, we need a whole new mindset, a new architecture built for this reality. And that architecture is called Zero Trust. Let's just put these two side by side. The old model was all about trust. Once you got past the firewall, you were in. The network basically trusted you, and you could often move around freely. Zero Trust, it throws that whole idea in the garbage. It operates on one simple principle: assume nothing is safe. It's all about constant, explicit verification. It's not about where you are on the network anymore, it's about who you are. Every single microservice has to prove its identity and be authorized for every single thing it tries to do. This is the mantra. You'll hear it everywhere. Never trust, always verify. It's that simple, but it's a massive philosophical change. We stop assuming something is safe just because it's inside. Instead, every single thing, every user, every device, every app, every network function has to prove itself over and over again before it gets access to anything. Trust is never a given. It has to be earned constantly. So how do we actually do this in a 5G network? Well, here are the key tactics. First, that network slicing we talked about, that's a huge security tool. We enforce strict isolation between slices, so if one gets breached, the damage is contained. It can't jump to another slice. Second, we encrypt everything, everywhere, all the time, end to end. Third, we practice that continuous verification, using strong digital identities for everything. And finally, because the system is just too complex for humans to watch, we use AI and machine learning to monitor everything in real time, looking for weird behavior that older security tools would totally miss. So, where do we go from here? It's important to remember that all of this, the cloud-native architecture, the zero-trust security, it isn't the final destination. Not at all.
It's really just the foundation for what comes next, for the whole next decade of how networks will evolve as we move beyond 5G. You can see that evolution right here. We started with the foundational 5G, which gave us the SBA and slicing. Right now, we're moving into what's called 5G Advanced. This is where we start baking AI and machine learning deep into the network's core and really optimizing it for things like extended reality, that mix of AR and VR. And when we look even further down the road to 6G, well, the vision there is for a network that isn't just using AI, but is built on AI. A network where zero trust is just the price of entry, and communication starts to get semantic, where the network understands not just the bits and bytes, but the actual meaning and intent behind them. And that brings me to one final thought, a question to really chew on. As these networks become totally intelligent, fully programmable, almost autonomous, does the nature of our biggest security threat change? Maybe the biggest danger isn't going to be the external hacker trying to get in anymore. Maybe the biggest risk will be the internal policies we write, the AI models we train, and the automated systems we build to govern it all. The network of the future is going to be incredibly powerful, but whether we can actually trust it, that's going to depend entirely on how we answer that question.